Hello everyone, I'm Amit Datto and today I'm presenting my work titled Autonomous Ship Navigation Using Reinforcement Learning in Unity Adhering to COLREG Regulations. This is how my presentation goes. First, I will discuss the introduction, then the problem statement. After that, I will discuss some of the previous work on this topic. Then I will discuss the proposed methodology. Then the result analysis and conclude with a conclusion and future work. Autonomous ship navigation is rapidly developing field with the potential to revolutionize the maritime industry. This concept is gaining importance due to the increasing complexity of shipment routes and the rise in maritime accidents attributed to human error. The advancements of autonomous ship navigation system for ships is seen as a crucial step towards enhancing maritime safety and efficiency. These systems are designed to predict potential risks from dynamic obstacles like other ships and provide collision-free path, ensuring robust navigation. Here we can see a graph. In the graph, the green circle represents the own ship and the red triangle represents the target ship that poses a risk of collision with the own ship. The objective is to reach the green triangle, which is our destination, while avoiding the target ship. This problem becomes more complex as the own ship must follow the international nautical rules of the road while avoiding the target ship. Now, as first, let's take a look at the rules. With information on our speed and heading, the target speed, heading, and the target angle, and the CPA range and time, we can assess a risk of collision. Once we have assessed that there exists a risk of collision with the ownership, action depends on the type of scenario. Assuming there is a risk of collision when the target vessel crosses ownership in the scenario above. Rule 15 of the Nautical Rules of the Road specifies that the target must maneuver to avoid a collision with on-ship. In other words, the target should give way to on-ship. Moreover, on-ship should maintain course and speed, that is, on-ship is stand-on vessel. In this case, the same rule applies, but now we, the on-ship, are the giveaway vessel and must maneuver to avoid a collision with the target ship. Rule 13 applies when one vessel overtakes another. In this first overtaking scenario, we maneuver, that means we turn to starboard to avoid the target that we are overtaking. We are mainly using reinforcement learning. So reinforcement learning is a machine learning approach where an agent learns to make decisions by interacting with an environment to maximize cumulative rewards. The agent observes the current state, takes action, receives feedback in form of a reward, and transition to a new state. Over time, by exploring various action and updating its policy based on the received rewards, the agent improves its strategy to achieve better long-term outcomes. This iterative process continues until the agent's behavior converges to an optimal policy. There are multiple works on obstacle avoidance with deep Q learning. There is another work that tries to do pathfinding and obstacle avoidance for unmanned surface vehicles using deep reinforcement learning. There's one more paper regarding COLREGs, ship collision avoidance, where they have used potential fields and velocity obstacles. In this scenario, the whole ship heading is 300 degrees and target's 1 relative bearing is thus 22 degrees. Target's 2's relative bearing is 183 degrees. Since relative bearing tells us the target direction relative to own ship's heading, we use relative bearing in our study. Knowing the relative bearing and the distance of the target vessel provides information to help assess the risk of collision. Remember, assessing risk of collision is important since the nautical rules of the road only deal with the target that we assess to have a risk of collision with our own ship. Now let us look how to find the target angle of a vessel. Here the black vessel is the own ship and the green vessel is the target vessel. Now if we draw an imaginary line at the target vessel heading, which is denoted by the red dotted line, and also we imagine a line from the target vessel and the ship, which is denoted by the blue, the target angle target angle is difference between the two lines denoted by brown. Here, in this scenario, the target angle is 30 degrees. Before discussing the proposed methodology, it's essential to understand three crucial components in a reinforcement learning environment: state, action, and reward. Now, at first, let's talk about the state. Our states includes the x, y, z coordinates of both the own ship and the target ship. This information helps the agent determine the location of the ships. Additionally, we include the relative bearing and target angle, which indicate the direction in which the ship is moving and whether there is a risk of collision with the own ship or not. So that's our state. Now let's talk about the action. While we could use a continuous action space with a values between 0 and 360, this approach would make the model complex and difficult to converge. Instead, we have divided the 360 degrees into 17 discrete angles, simplifying the problem and making it more manageable for the model to solve. So that's our action. Now let's talk about the reward. The reward function is designed to encourage the ship to avoid collisions while following international nautical rules. We use the Euclidean distance between the own ship and the destination to provide a primary reward. Additionally, we give a small reward for moving to starboard, as maritime rules generally dictates that ship should move to starboard to avoid collision. If a collision occurs, we deduct 200 points from the reward. This structure ensures that the agent learns to navigate safely and efficiently. Now let's talk about the proposed method. We are primarily using proximal policy optimization algorithm to train our agent. At first, we can see in the diagram that we have two different networks. The goal of the policy network is to take observation as an input and then output action probabilities. The goal of the value network is to estimate how good an action is based on the state. So the value network will take the state and action as an input and it will output estimated reward. So the flow goes like this. At first, the agent will take action on the environment based on the state. Then the reward is being calculated. After that, we have experience tuple where we are storing the state, action, reward, and the next state as an array. After storing the experience tuple, these data are being used to train the network. Since the value network is estimating the reward and we have an actual reward, so we'll calculate the loss and propagate it through the network. And for the policy network, it has a clipping function which checks if the updated policy is too much different from the previous policy. If it finds that the policy update is not significant, then it updates the policy network. If the policy update is significant, then it will not update the network. Now let's talk about the result analysis. We trained the agent using three different scenarios. In this scenario, the target ship is moving in the same direction as the own ship, and the own ship wants to overtake it. As you can see, the own ship successfully avoids the target ship and reaches its destination. The black dotted line denotes the path that the agent took to reach the destination. Now this is the crossing stand-on scenario. As we can see that own ship successfully avoids the target ship and goes to the destination. Lastly, this is a crossing giveaway scenario and one ship successfully avoids the target ship and reaches its destination. The main thing is that all of the scenarios, the agent complies with the international nautical rules of the road. In this table, we can see that we ran the model 10 times for each scenario and one ship never collides with the target ship. Also, the third column describes the lowest average distance between the own ship and the target ship. So in conclusion, we have proposed a new method for COLREG ship collision avoidance. In the future, we want to train the agent for all different scenarios. We also want to test the model in a traffic scenario where multiple ships are present and see if our model can avoid the ship that are currently around, and can it successfully reach the destination while avoiding all the other ships. Thank you everyone.